We'll now discuss more about how the memory and the cache of our system is set up. Memory is the functional unit of a computer that stores and retrieves the instructions and the data that's being executed. Now, all information stored in memory is represented internally using the binary numbering system that we've previously talked about. Computer memory actually uses an access technique that we call random access. And the memory unit is frequently referred to as random access memory, or just RAM. Now, it's worth noting that RAM has three characteristics. The first one is that the memory is divided into fixed size units that we call cells. And each cell is associated with a unique identifier, which we call an address. Now, these addresses are the unsigned integers 1, or I should say it starts at 0, 1, 2, all the way to the maximum address that's available in our RAM. The second characteristic is that all accesses to memory are to a specific address, and we must always fetch or store a complete cell. What that means is all the bits in that cell, we're talking about all of them, okay? The cell is the minimum unit of access, so we can't just like partially store something in a cell. We store something completely within a cell. It's not partial. It's either everything fits in there or none. Now, we might need multiple cells to store something, and that's okay, but we can't partially store something in just a cell. The third characteristic is that the time it takes to fetch or store the contents of a cell is the same for all cells in memory. It's not the case where if I'm at this address, it takes so long, and then if I store something in a different address, that it takes longer or shorter. The access time for any cell in our memory is going to be the same amount. Now let's talk about memory cells for just a minute. Now, each cell in our memory has a fixed number of binary digits. So what that means is the number of bits per cell is what we call the cell size, and we denote this as W. So this size will actually tell us the largest possible value that a cell can hold. So for example, if W is 8, then that means that we can have 8 bits for a single cell, which means that the largest unsigned integer would be 1111111, 8 ones, which comes out to 255. If we want to store larger values, we would need multiple cells. And like I said before, that's okay. It's okay if we need multiple memory cells to store a single value. It's just worth noting that a single cell can store so much. In most systems, the cell size is going to be 8 bits. Now let's talk about memory addresses. So each cell in our RAM is identified by a unique unsigned integer address. So this would start at 0, 1, 2, 3, and so forth. Now, if we have n bits available to represent the address of a cell, then what we find is that the maximum memory size is 2 to the n power. Now, obviously, the smallest address is going to be 0 if we start at 0. But the whole point here is that the memory addresses would actually range from 0 all the way to 2 power n minus 1. And that's because we can use the string of bits to represent each address. So this means that we get a wide range of addresses available. In fact, this 2 power n gives us the total number of memory cells. It also tells us the maximum memory size, or what's also considered the address space of the computer. Now, typical values of n back in the 60s and 70s would be something like 16, 20, 22, 24. But today's computers have at least 32 address bits, which means we allow for up to 2 power 32 addresses, or memory cells, I say. We have 2 to the 32 power addresses, and that's a lot. So when you think about our RAM size here, that's practically almost 4 billion memory cells, or what we would consider 4 gigabytes of RAM. Now, some systems now support 64-bit addresses, and that means that the maximum memory is theoretically 2 to the 64 power bytes, or this would come out to 17 million gigabytes. Good luck trying to add enough RAM to actually meet the 17 million gigabytes. In fact, most motherboards only go up to like 16 or 32 gigabytes of RAM realistically. So I don't think we're ever going to hit that 17 million gigabytes anytime soon. So let's take a look at a simple example of how our memory could be laid out. So here's one such example. So what we have here is this set of contents. So we have all of our data in here, and every single cell in here and the data that's in these cells can either be instructions, it could be some kind of data, it could be several different things. And then we also have an address for each of these memory cells. So we can think of these as a unique location for each of these data. And here in our example, we have addresses 0 to 999, but realistically, we have a lot more than 1,000 addresses available to us. Now, it's important to note that each cell and the data stored in there is a sequence of zeros and ones. So like if we store -26 here, for example, this right here, we don't actually store the negative sign, a 2 and a 6. It's actually stored as a sequence of zeros and ones. And because that's the only way that the machine can actually read values in our memory. And then it's up to the program to be able to interpret those zeros and ones to determine what the actual data is. So to give you an example, we might have like 001001110 that's actually stored in a memory cell. There are two basic memory operations, which we call fetching and storing. So fetch, the way it's set up is we kind of set up in this fashion right here. It's kind of like the formal definition, where we have fetch and then we have an address in parentheses, and then we assign it some value. The idea with this is that we're going to fetch a copy of the contents of the memory cell with the specified address. And then we're going to return those contents as the result of the operation. So we're looking up a particular address, we get the contents that's in that address, and we store it in this value variable. The second operation is called store, and the way it's set up is we have the word store, and then in parentheses we have an address and the value. And the way this works is that we're going to store the specified value into the memory cell that's specified by the address. Now, what makes this a little bit different from the fetch operation is that the contents of the memory cell that we store the value in that were previously there are lost. So with fetch, when we retrieve something from a particular address, the contents in that address stay there. It's not like we remove it and then put it into a value. We think of it more as a copy, whereas with store, we're going to just overwrite whatever was in the cell with the value that we pass in here. There is still one other component of memory that we haven't talked about yet, and these are what we call registers. So a register is just another storage cell, so it does store things, but it's not part of the main memory unit. It's separate from it. It's actually a lot faster to access stuff from there, but the whole reason why we're talking about this is because in order to do the fetch and store operations, we use registers to store the address and the value of the for fetching and storing. Because remember, we talked about an address and a value. So we use registers to store those values, or the contents in those variables. So the memory unit actually has two special registers whose purpose is to hold these two operands for fetching and storing. We first have the memory address register, or MAR. This holds the address of the cell that we're going to access. Now, the MAR must be able to hold any address, so it has to be at least n bits wide, where 2 power n is the address space of our computer. The second register is the memory data register, or the MDR, and this contains the data value that is being fetched or we're actually going to be storing. Now, we might think that, okay, that means the MDR should be W bits wide, where W is the cell size. But for most computers, as we mentioned before, the cell size is only 8 bits, and usually we're going to need to be able to handle larger values. So the size of the MDR is usually some multiple 8. In most cases, the width is going to be like 32 bits or 64 bits, and this will allow us to fetch either an integer or a real value in a single step, which is very efficient for us. So with these two registers, we can describe a little bit more about what's going on when we're fetching and storing. So whenever we're fetching, we're loading the address into the MAR, and then we decode that address. So we've got to figure out exactly what address we're talking about. And then we'll copy the contents of that memory location into the MDR. Now when we're storing, we're going to load the address into the MAR, we're going to load the value that we're going to store into the MDR, and then we'll decode the address that's in the MAR, and then finally we'll store the contents of the MDR into that memory location. Now, it's worth noting that we talked about decoding an address. So what are we talking about here? It means that the memory unit must translate the n-bit binary address that's stored in the MAR into the set of signals that we need to access that one specific memory cell. So this is where the decoder circuit comes into play, because each output line would be a specific memory address. So we can use the signals we talked about before to determine exactly which address do we want to store something into or to retrieve something from. Now, let's suppose we execute the same instruction several times. I'm not saying like it's going to be repeatedly. I mean, sometimes it's repeatedly, but we're using the same instruction quite a bit in our program. One of the bottlenecks is going to be the fact that we spend a lot of time retrieving the instruction from main memory. Because, I mean, while it is pretty quick to get stuff from our main memory, it can become a bottleneck when our instructions are being executed so fast that we're spending more time just fetching and storing stuff in memory than actually executing stuff. So what developers have done to help decrease the memory access time is that they constructed another type of memory unit, a high-speed memory unit, which we call the cache memory. And the idea with this is that we'll take a recently used instruction and store it in the cache, because if we have used the instruction, there is a good chance that we're going to run that instruction again. So if we keep getting stuff from this cache, which is faster to access than our memory, then our programs are going to run faster. So the idea is that whenever we execute an instruction, we'll check the cache first. And if the instruction is there, then let's just go ahead and grab the instruction from that cache. And like I said, this is going to be a lot faster to access than main memory is, so it speeds up our execution time. Now, if it's not there, then we'll just grab the instruction from main memory. And you might think, well, do we lose some time by checking the cache first? Maybe just a little bit, but the amount is so insignificant that it doesn't really hinder our performance of our programs if we spend some time checking the cache first. So it's perfectly okay to check the cache first. Now, one of the things that you might be thinking is, well, why don't we just put everything in the cache then? Why use the RAM if we can just use the cache to access stuff quicker? While the cache is faster than RAM, it's also a lot smaller than RAM. The cache may be a couple megabytes, whereas the RAM could be several gigabytes. So we can store a lot more stuff in our RAM than we can in the cache. So we can't put everything in the cache, but we can put the most recently used stuff into the cache, and then we can just check it. And then as we execute more instructions, we can update our cache and maybe overwrite some stuff. The idea is just keep storing the most recently used instructions and data in our cache, so that way we can speed up our programs if we do encounter that same stuff pretty soon.